Today I'll talk about drawing molecular structures. There are different kinds of molecular structures. You have the Lewis dot structure, the Kekule structure, the condensed structure, the bond line structure, and the 3D hashed and wedged structures. So let's start with the Lewis dot structure. So I have the Lewis dot structures of the common atoms that are used in organic chemistry. You can see this is hydrogen, lithium, sodium, and potassium. And this dot represents the valence electron. So hydrogen has one electron in its valence shell, so does lithium, sodium, and potassium. Each of them have only one electron in the valence shell. In case of magnesium and calcium, they have two electrons in the valence shell. For boron and aluminum, they have three unpaired electrons in the valence shell. For carbon and silicon, there are four unpaired electrons in the valence shell. 1, 2, 3, and 4. In case of nitrogen and phosphorus, there are 5 electrons in the valence shell, 3 of which are unpaired, and this is the lone pair of electrons. What it means is that whenever you see unpaired electrons, each unpaired electron can form one bond. So, for example, hydrogen has one unpaired electron, it can form one bond. Magnesium has two unpaired electrons and it can form two bonds. Boron has three unpaired electrons, so it can form three bonds. Carbon can form four bonds. Nitrogen can form three bonds. In case of oxygen, two single electrons, so oxygen can form two bonds. All halogens have only one unpaired electrons in the valence shell. Each of the halogen atom can form only one bond. Phosphorus and sulfur are unique. Although you can see that there are three unpaired electrons in phosphorus, it can form more than three bonds because it has d orbitals and to allow for hybridization. Sulfur, in case of sulfur, there are only two unpaired electrons, but it can also form and expand its valence shell by hybridization, and so it can form more than two bonds. And we'll see examples for phosphorus and sulfur. What you see right here is the electrons in the valence shell, and the number of unpaired electrons is equal to the number of bonds that the atom can form. The exception is phosphorus and sulfur. So let's look at the rules for drawing Lewis dot structures of molecules. There are four rules. The first rule is to draw the molecular skeleton of the molecule, ion, or radical, and that's based on the Lewis dot structure of each atom. So look at the table of Lewis dot structure and arrange the atoms in such a way so that if the atom can form only one bond, then it should be only next to one atom. If the atom can form two bonds, then it should be next to two atoms. If the atom can form three bonds, then it should be next to three atoms, and so on and so forth. The second step is to add up all the valence electrons of each and every atom in the molecule. And to this total, you add +1 if the ion has a negative charge, -1 charge, and you add -1 if the charge on the ion is +1. And then each of the bond is equal to 2 shared electrons. We need to maximize the number of atoms from the second row that have a complete octet. Remember that hydrogen can have only a duet of electrons. Elements in the third row like phosphorus and sulfur can have more than 8 electrons because they can expand the valence shell. If it's a radical, then you'll have a single electron on an atom, and we'll come across that too. Then we need to assign the charge on each atom. If the number of electrons on the atom is more or less than the number of electrons in the original atom. And this is the formula which you need to follow, and that is the charge on the atom is equal to the number of valence electrons minus the number of unshared electrons minus half the number of bonding electrons. So most important thing to remember that in a molecule, each atom can donate or share or accept electrons to complete the valence shell. So let's take a simple example of hydrogen. Hydrogen has 1 electron in the valence shell. It can donate the electron to give a H plus, or it can accept an electron to form H minus, as seen right here. Or it can share its electron, as in case of hydrogen molecule. So this is the Lewis dot structures of the atoms that we had looked earlier. Let's do some examples where we can draw the Lewis dot structure of a molecule. Let's start with sodium hydride. NaH is sodium hydride. So sodium, if you look at this table, this is sodium. It has 1 electron in its valence shell. And hydrogen also has 1 electron in the valence shell. So sodium donates its electron to hydrogen, and so hydrogen has a negative charge and sodium has a positive charge. Let's look at another example of HF. In case of HF, hydrogen has, you arrange the atom, well, there's not much options here. You can just put H and F. That's the only way you can arrange it. Hydrogen has 1 electron and fluorine has 7 electrons in its valence shell, but it has only 1 unpaired electron. So this unpaired electron can be shared with the hydrogen. As you can see here, the two red dots are the 2 electrons which are shared between the 2 atoms. And this forms a polar covalent bond because of the electronegativity difference. You can check my video on polar and non-polar covalent bonds to better understand why this is a polar covalent bond. Let's look at the example of calcium chloride. So in case of calcium, so how do we arrange the calcium and the 2 chlorine atoms? So I have arranged it in like chlorine, calcium, and chlorine in this order. You could also try some different order like calcium, chlorine, and chlorine. But you'll observe that the reason calcium is in the center and chlorine are on each side is because calcium has 2 unpaired electrons and chlorine has only 1 unpaired electron. And so each chlorine atom can share its electron with calcium, but since calcium is electropositive and chlorine is electronegative, so calcium will donate its electron to chlorine, and so calcium will have 2+ charge, and each of the chlorine atoms will have a minus charge, and so it's the chloride ion. So let's look at more examples to learn how to draw the Lewis dot structure of a molecule. I think it's a good idea to kind of memorize the valence shell electrons for these atoms, because you'll come across these in organic chemistry class. So let's start with an example. Phosphoric acid. The molecular formula is H3PO4. So we need to arrange these atoms in step 1 such based on the number of electrons in the valence shell and how many bonds each atom can form. For example, hydrogen has 1 electron, so it can form 1 bond. So if you recall, based on step 1, hydrogen has only 1 electron, so it's next to only 1 atom, which is oxygen. So you can see all the 3 hydrogens in this case are next to only 1 atom, and that's the oxygen atom. In case of oxygen, there are 2 unpaired electrons, so it can form 2 bonds. So oxygen should be next to only 2 atoms. So let's look at this one. So oxygen here is next to hydrogen and phosphorus. This oxygen is next to this hydrogen and phosphorus. This oxygen is next to this hydrogen and phosphorus. And then you have this oxygen by itself, just next to phosphorus. So this is a unique situation. When this happens, then you have to think of a double bond, and this happens because phosphorus is a period 3 element and it can expand its valence shell. So the next step is to write down the number of valence electrons in the molecule. So let's start with phosphorus. There's 1 phosphorus atom, and there are 5 valence electrons in each phosphorus. So right here you can see 5 valence electrons, and so you have 5 electrons from the phosphorus. There are 4 oxygen atoms, so 4 multiplied by 6. 6 is the number of electrons, valence electrons right here. And so 4 times 6 is 24. And then you have 3 hydrogen atoms. 3 times 1, 1 is the number of electron in the hydrogen valence shell. And so you have 3 electrons from hydrogens. So you add 25 plus 24 plus 3, and you get a grand total of 32 electrons. So there are 32 valence electrons in the molecule. So each bond is represented by 2 electrons. So between oxygen and hydrogen, you can see this 2 red dots means 2 electrons, and these are shared by oxygen and hydrogen. And so between each of the atoms, you put 2 electrons, and in this case I've put red, the 2 electrons which are shared by the 2 atoms. So between hydrogen and oxygen, this is the pair of electrons, red, and then between oxygen and phosphorus, this is a pair of electrons that's shared. So once you have arranged all that, you will basically also put the electrons around oxygen. So let's start with phosphorus. So in case of phosphorus, you have 5 electrons, and you have 1, 2, 3. So these 3 electrons have formed a bond with these 3 oxygen atoms. and then it leaves a lone pair of electrons right here. So these lone pair of electrons, due to hybridization, can form a double bond, and so there are two pairs of electrons, red dots right here, that indicates two bonds between phosphorus and oxygen. And then the two lone pair of electrons around oxygen are written as is. So that's how you put the electrons around, and all these need to add up to 32. So let's make sure that it is 32. So you have 2 plus 2, 4. 4 plus 4 is 8, and 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So there are 32 electrons. So all the electrons have been accounted for. There is no charge on phosphoric acid, so we don't have to go to step 4 to assign any charges. On the atoms, let's look at a second example, which in this particular case there is a charge on the molecule. This is the acetylide anion, HCC, and this is the charge. It has a negative -1 charge. So the first step is to arrange the atoms in such a way that based on the number of bonds each atom can form. So hydrogen can form only one bond, and then the two carbon atoms can form 4 bonds each based on the lowest dot structure of atoms. So this is the only way it can be arranged. So hydrogen is next to only one atom because it can form only one bond, whereas carbon is next to another carbon because it can form a maximum of 4 bonds. So the step 2 is to count the number of valence electrons in the whole molecule. So let's start with hydrogen. We have one hydrogen atom. You multiply it by 1 electron per hydrogen, and so you get a grand total of 1 electron. There are 2 carbon atoms, so 2 multiplied by 4. 4 is the number of electrons in the carbon valence shell, and you get 8 electrons. Now the charge is -1. This is the charge on the anion. So charge is -1. That means it's 1 electron. And so we have a total of 8, 9, 10. 10 electrons. There are 10 electrons in the valence shell. So between hydrogen and carbon, you put 2 electrons because it can form, that's 2 electrons represents 1 bond. And then you have 2 electrons on the last carbon because a -1 charge is equal to 2 electrons. And then you put the rest of the electrons between the 2 carbons. So you have 2 here and 2 here, so that's total of 4. So 10 minus 4 is 6, so you put the rest 6 of the electrons between the 2 carbons, and this represents a triple bond. So the next step is to allocate the charge. So in order to allocate the charge, you have to use the formula: electrons in the valence shell minus the unpaired 2 in this case, and then half of the bonding electrons. So there are 6 bonding electrons between the 2 carbons, and then you get an answer of -1, and so you put -1 charge on the carbon. So that's how you draw the Lewis structure. So let's look at additional examples. So we have 4 examples here, 1, 2, 3, and 4. We have methylamine, and then this C2H6S can be dimethyl sulfide or ethyl. The 2 separate molecules, and then you have benzene. This is a little bit complicated. And then you have dimethyl sulfate. Di means 2 methyl groups. This is a methyl group, CH3, and this is the sulfate. So based on the Lewis dot structure of atoms and based on the rules that you have learned, try to draw the Lewis dot structure of the molecules. So remember, the first step is to arrange the atoms based on the number of bonds each atom can form. So once you have drawn the Lewis dot structure, you can check the answers. So let's start with methylamine. In this case, there's hydrogens right here, and each hydrogen, as you're aware, can form only one bond, and so it should be next to only one atom. So the arrangement should be like this. So this hydrogen is next to carbon, this hydrogen is next to carbon, this hydrogen is next to carbon, and this hydrogen is next to a nitrogen, and so is this hydrogen. And carbon and nitrogen are next to each other. Carbon is next to 4 atoms, 1, 2, 3, 4, because it can form 4 bonds. Nitrogen is next to 3 atoms, 1, 2, and 3. So the bonding pair of electrons are red. So, and this is the lone pair of electrons on nitrogen. So this is the correct Lewis dot structure. Let's look at dimethyl sulfide. In case of dimethyl sulfide, you can have carbon, and next to the carbon you can have 3 hydrogens and 1 sulfur. The reason this arrangement is good is because, as you're aware, hydrogen can form only 1 bond, so hydrogen always needs to be next to only 1 atom. Sulfur, if you recall, has 2 unpaired electrons, and so it can form 2 bonds, so it's next to 2 carbon atoms. It also has the 2 lone pair of electrons, which are in black color. So this is how you draw the Lewis dot structure of dimethyl sulfide. Let's look at ethyl. In case of ethyl, you can arrange it in this way, where you have 2 carbon atoms next to each other, and then sulfur is next to just 1 carbon. So in this case, the sulfur can form, has two lone pair of electrons right here, and it has 2 unpaired electrons which can form bonds, with one with hydrogen and other one with carbon. And each carbon atom it's around 4 atoms. Even this carbon atom is around 4 atoms, 1, 2, 3, and 4. So this is how you draw the Lewis dot structure of ethyl. Benzene is a little bit complicated. It will take some time for you to figure it out, but it's a cyclic molecule, and each carbon in this case is next to only 3 atoms. So this carbon is next to a hydrogen, a carbon, and a carbon. And there is a double bond between the 2 carbons. So there are 2 pairs of electrons right here, 2 pairs of electrons right here. So there are 3 double bonds in this structure. And as usual, a pair of electrons represents a single bond. Let's look at the example of dimethyl sulfate. So in this case, as you're aware, sulfur can expand its valence shell. So you place sulfur in the center and you have carbon right here, and next to the carbon you have 4 atoms, 1, 2, 3, and 4. And oxygen is next to the sulfur. So sulfur has, around sulfur you have 4 atoms, 4 oxygen atoms. And since sulfur can expand its valence shell, that's the reason it has more than 8 electrons around it. So it has 4 plus 4, 8, 10, 12. It has 12 electrons around it. And so that's allowed. It's allowed only for phosphorus and sulfur. All other atoms should have only 8 electrons around it, and hydrogen should have only 2 electrons around it. So you can see in this case each oxygen atom has 8 electrons. If you look at this oxygen atom, it has 8 electrons. 4 plus 2, 6 plus 2, 8. If you look at this oxygen atom, it has 8 electrons. So, and carbon atom also has 8 electrons around it. So that's how you draw the Lewis dot structure of dimethyl sulfate. And I have a model here this is for methylamine. This blue atom is the methylamine, is nitrogen, and the black is the carbon atom, and this white are the hydrogens. So you can see this pink bonds, they are one pair of electrons that are shared between carbon and hydrogen. So even this pink bond is a pair of electrons that's shared between hydrogen and carbon. Same is the case with the nitrogen. And there is a bond between carbon and nitrogen. Nitrogen is blue and carbon is black. So you can kind of, draw a model. This is the bond structure, and we'll kind of learn more about it. Let's look at another set of examples. And once you have written down the Lewis dot structure of the molecules, you can check the answers. So in this case, we have a neutral molecule, and then this is a radical, and this is an anion. So these are the answers. So you can see this structure is already kind of given, so you kind of write it as it is. So each carbon atom has 4 atoms around it. Bromine can form only one bond, and so it has only 1 atom around it. Oxygen, in this case, it can form 2 bonds, but it forms a double bond with the carbon atom, so it has only 1 atom next to it. So this is how you draw the Lewis dot structure for 2-bromobutanol. In case of N-propyl radical, you follow the same structure, and then you put a pair of electrons between each atoms, and there's 1 single electron on the end carbon atom. In case of borane, you have boron is in the center, and boron has 3 unpaired electrons. It can share with each of the hydrogen atoms, and that's how you draw the Lewis dot structure. In case of enolate anion, the negative charge is here, right here on carbon. And for each of the atom, let's consider this carbon atom, it has a complete octet. Let's consider this oxygen atom, it has a complete octet. So each of the atoms has a complete octet, and each of the hydrogen has a duet. So that's how you draw the lowest start structure of the enolate ion. This electrons can jump onto the oxygen, and this negative charge can form a double bond between the two carbons. And that's the topic of resonance, and please refer to my video on resonance structures to learn more about the resonance. So there are different ways to depict molecular structure. In addition to the Lewis dot structure, chemists have developed methods to write molecular structures, because it's pretty difficult to write a Lewis structure for large organic molecules. And so they came up with a Kekule structure. Kekule came up with this structure. It's also called the Lewis bond line structure, in which each bonding or shared pair of electrons is represented by a single bond line. So let's look at an example. So in this case, the red lines represent the shared pair of electrons between the two atoms, whereas the lone pair of electrons are shown in black. For example, in case of oxygen, there are two lone pair of electrons, and there are two bonded pair of electrons. In case of bromine, there are three lone pair of electrons and one bonding pair of electrons. Another way to write is the molecular structure is called the condensed molecular structure. In this case, you don't draw the structure like this, like the bond. You just write it in a single line. So all the atoms associated with each carbon atom is written next to it. In this particular case, the carbon is attached to 3 hydrogens, so you write CH3. This carbon is attached to 2 hydrogens, so you write CH2. This carbon is attached to hydrogen and bromine, so you write CHBr. Whereas this carbon is attached to hydrogen and an oxygen, and you write CHO. Alternatively, you can just make a bond right here next and put a Br there, and that's fine too. So that's called the condensed molecular structure. Another way to write the molecular structure for the same molecule is the zigzag. This is called the zigzag line, and it's called the abbreviated bond line. So in this case, the end of each line is the carbon atom, unless a hydrogen is written next to it. The hydrogens attached to the carbon are not shown. So let me show an example. This is the molecule. So this red is the oxygen atom, this is the hydrogen, this is the carbon, and then you have the bromine, which is green, and this is carbon-bromine bond, and this is the carbon atom, this is the hydrogen. So the reason you draw this zigzag structure is, if you look at this looks like a zigzag. So carbon atoms are arranged in a zigzag in a molecule, and so that's the reason when you write the abbreviated bond line structure, the carbon skeleton is written in a zigzag format. The hydrogen atoms on the carbon are not shown. So this is the abbreviated bond line structure. Another way to draw the molecule is in 3D form, to show whether the bromine atom is behind. In this case, the hashed line means it's behind, and the solid line means it's towards you. So let's look at the same example which we have. So you can see this is the bromine atom right here, and it is facing me. So it will be the wedge solid line. And if you kind of change, switch the molecule like this, now the bromine atom is away on the other side, and so it will be represented by the hashed line. So it's good to learn the concepts of the wedge and the hashed lines. You'll come across it in chiral molecules. So this is the hashed means bond is behind, and wedge means bond is in front, and solid line means its bond is in the plane of the paper. So let's look at another example. This is a radical, and this radical, you can see for the Lewis bond line or the Kekule structure, you show a single solid line for each bonded pair of electrons, and the radical single electron is shown on the carbon. In case of the condensed form, you just write it as CH3. Similarly, this carbon is attached to 3CH3, so you write CH3. Then this carbon is attached to deuterium and hydrogen, so you write CHD. Then this carbon is attached to 2 hydrogens, so you write CH2. And then you put an electron on top of the carbon to indicate that it is a radical. For the abbreviated bond line, you draw the carbon skeleton in zigzag format. So end of the line is a carbon here. There's a carbon here and this carbon. So that's these 3 carbons, and this carbon has a single electron. And this is the center carbon, which is attached to a deuterium. So this is the example. This is the model I have kind of drawn, made. This is the model I've made, and this green this is the p orbital. This is the p orbital, and it has a single electron in it. And this is how it looks like. You have the deuterium. This is deuterium, and this is the hydrogen. The hydrogen atoms are not shown in the abbreviated bond line, nor is the p orbital. We just put the single electron on the carbon. So yeah, so these are the 3 carbon atoms. 1 2 3 carbon atoms. And then you can also draw the 3D hashed and wedged structure, where you can show whether the deuterium is behind or in the front. So the deuterium can be towards you. In this case, it's towards you, and so this deuterium will be represented by a wedge, solid wedge line, whereas if it's away from you, this deuterium, then it will be represented by a hashed line. So that's how it's always good to draw models to look at the 3D structures. I have made this model from the Organic Chemistry Basic Kit, and it's sold by Maruzen. You can buy any models and definitely make the models, and so that it will help you understand the 3D structures of organic molecules and why the reactions happen in a certain way. So let's look at a final example. In this particular case, this is the case of dimethyl sulfide. Here again, each of the bonded pair of electrons is represented by a solid red line, and the lone pairs are just shown as is. And for the condensed form, you just write CH3. So this carbon is attached to 3 hydrogens, so you write CH3. Sulfur is by itself, and then you have another CH3 group right here. And this is the abbreviated bond line structure. So I've again made a model. This center atom, this is the sulfur atom, this is a carbon atom, and this is another, and these white are the hydrogen atoms. So you have three hydrogen atoms attached to each carbon atom, and the carbon atom is attached to the sulfur atom. So this is the structure of dimethyl sulfide.
Thanks for watching. Like and subscribe.